I'm going to start this lecture on uncertainty with a simple experiment. Let's say I want to find the gamma of some type of fluid. That's nothing more than the, or maybe let's even change it even one more level. Let's say I want to find the density of some type of fluid. The density is nothing more than the mass per unit volume. So obviously I need to measure the mass and the volume. But you don't really directly measure the mass, you measure the weight. So for my tools, here's what I'm going to need. I'm going to need a scale. And let's say we find a scale that's plus or minus, say, 3%. Not a great scale. Then we need some type of cylinder. And of course it'll have a length and a radius associated with it. I need a ruler. And let's say the ruler I have, let's say that, it has 5 inches and then 6 inches, but the measurements are quite thick here. So you don't, when you're looking at something and the measurement's this and you're measuring something this long, and say this is 5, well, is this 5 right in the middle or right over here? So let's say it has a plus or minus 3% error on it as well. Well, what else do I need? I need some type of device that will measure gravitational, the G. Now, this can be nothing more than some type of elevation meter. And it could be, say, in some GPS type device. And then we would have to look and relate the two. But let's say we're looking at G plus or minus, say, 0.5%. Now, how do we do this? Well, we have to remember what we're trying to find here. Let's go ahead and move some of this to the top. We're looking for density, so we're looking for mass per unit volume. Okay, so let's take off and propose an experiment here. You find your beaker. You come in, and the inside of your beaker, you measure the length, and then you measure the radius. Or better yet, you're probably measuring the diameter. So you're measuring the diameter to plus or minus, since my ruler is measuring it, it's 3%, plus or minus 3%. So you calculate the volume in there as the diameter times, or here, pi r squared, or diameter squared divided by 4, and then you multiply that times the length. So you get your area across the top. That gives you your volume. Now you go over to your scale, some type of scale. You put this on the scale. So it measures what I'm going to call Z, or the 0, to be, let's say that this thing measures, and I'm going to use, since I'm in the English systems, I'm going to use that my beaker weighed 4 pounds. But that's got to be plus or minus what? 3%. Now I go back in and I fill it with my fluid. And I put it back on the scale. So here's what I'm going to call this WZ. And let's say it measures that to be 30 pounds, plus or minus 3%. Now, along the way, I took my ruler, and in my ruler, I basically measured a diameter of, say, 1/2 foot, plus or minus what? 3%. Let me change this from a 3% on the scale to something that's 4% so that you'll see that so we're going to make this scale be a 4% scale. So I measured my diameter plus or minus 3%, and that's going to be squared over 4 times my length, which is, here's my scale. Length is, let's see, I said that was a half. Let's say this is 0.75 plus or minus 3% there. Now my final equation is, I need to measure my gravitational. So I'll say my gravitational is 32.1 plus or minus 0.5%. So since the weight is equal to mg, then the mass is equal to the weight divided by g. So I'm looking for the density, being the mass per unit volume. This is the mass of the liquid. Well, the mass of the liquid is going to be the weight of the Z minus Z, because you've got to subtract off the weight of the container. So this is the weight of the container. This is the weight of the container and the fluid in the container. Now this is the total weight, but I need to divide that by G, and I need to divide that by volume. So now here's what I get. Rho is equal to, now let's take WZ. Okay, it's nothing more than WZ minus Z. I'm going to go ahead and put my numbers in without the percent. So I'm going to go ahead and do this, okay. 30 pounds, well, I'll go ahead and say plus or minus 4% minus, and I'll put this in parentheses, Z, well, that's 4 pounds plus or minus 4% over G, which was 32.1 plus or minus 0.5%, and then volume was all of this. And so here's my volume stuck in here. Now, here's what I'm going to do first. I'm going to start borrowing a Matlab session. And here I am with the Matlab session, and what I'm going to do is I'm going to list these. WZ is equal to 30. Then I'm going to say Z is equal to 4. I'm going to say G is equal to 32.1. L was equal to 0.75. Diameter was equal to 0.5. And I'm going to say, there are my values. Now I'm going to say rho was equal to WZ minus Z. Now I need to put parentheses around this. And I'm going to divide that by G, and I'm going to divide that by the volume. Now the volume I have failed to do, so here's what you're going to find. Undefined value was the volume. So my volume is going to be equal to pi times d squared divided by 4 times L. Try that again with a pi in there. So there's my volume. Now I go back up 2 or 3, and now I'll end up with the value 5.5002. 5.5002. But at plus or minus what? How do you carry these in here? There's uncertainties in your measurements all the way through here. And if you wanted to, you can look at them like this. Here's your uncertainties. Now, there is a prevailing mentality, and there's nothing wrong with this, that you can calculate your uncertainties using differential methods. And it works pretty much okay. But if you were looking at this, these uncertainties would be related to one simple fact. Let's take a look at this. What is the density a function of? Well, first it's a function of G. I guess I should list it a little bit differently. WZ, a Z, this term. I have G down here. Then I have D, and I have L. Now, it can get kind of complicated, but it's not that bad if you look at this, because you can realize that it's nothing more than WZ minus Z over G. Now I've got to carry this term in there, pi d squared over 4 times L. So if I had L, D, G, Z, and then WZ, then that's all I need. 1, 2, 3, 4, 5. Now it turns out, if you systematically go through this, let's start with the G, for example, squared. And then the uncertainty, you could list U, say G squared plus partial of rho WZ squared times the uncertainty in, I guess I have to do both of those squared, plus partial of rho with respect to Z squared times uncertainty in Z plus partial of rho with respect to D uncertainty in D squared plus one final thing U in L squared. Now, looks like a mess. However, I can go back and use Matlab for this, but we have to recognize one simple thing. Of all the equations you could be faced with, this is a fairly simple experiment. It's not that complex, and the equation itself isn't that bad. And let's take a look at what this mess of an equation turns out to be. You could say the uncertainty in rho. So let's go into Matlab and look at this. Now I could use another one. I could use Maxima or something like that. But for the sake of quickness and something that you have access to, let's do Matlab. Alright, so I'm going to do a clear, just to clear everything out. And then I'm going to say I want a symbolic variable WZ, Z, G, D, and L. Okay. Now, if you go over to the browser, which I'll break free and move it over to the workspace, what you'll see is I have created these terms here that are essentially symbolic characters. I mean, these are all symbolic. I've turned these into symbolic variables. They've listed as a symbol, and they have a funny box here. Let's see what we can do with those. Let's list row. Row's equal to, okay, WZ minus Z divided by G divided by, and now I'm going to close this thing off, pi times D squared divided by 4 times L, and you end up with a new symbol on there, mainly a row. What I mean by that is, let me show you. Before, these variables were defined in this symbol. The row was defined as a result of it as a symbolic variable, and it looks like that. Now, can we take a differential of this equation? Well, let's take a look. Let's say we wanted to take a differential of row with respect to, well, the first thing I need to do is take its differential with respect to G. The fact of the matter is, looks like I can. The problem is I need to figure out how to do substitution. But for right now, I'm going to say that we can go about this. Substitution can occur, though, in a simple form. Here's how a substitution can take place. Let's say we wanted to find this value, SUBS, substitute. But what we want to substitute in, and we got to pay close attention here, and I may have to move the window down in order to pick up my values from the upper. WZ, and I'm going to list them in the same sequence that are listed here, maybe. Let's do it that way. G, WZ, Z, D, and L. The values I want to substitute for those are going to be, and let me be very careful about this, 32.1, 30, 4, 0.5, and 0.75. Now, let me take a quick break here and show you what I actually am substituting and how this. First, let me hit the enter key, make sure that it'll work. Now, let me show you what I'm actually doing here. So, I essentially just took the differential of this value, which turned out to be this. And for the value of G, I want to substitute this. And for the value of WZ, I want to substitute that. The value of Z, I want to substitute that. I want to substitute that in that equation. The value of D, I want 0.5. The value of L is that. Now, am I correct? Let me make sure. WZ was 30. Am I right there? Yes. Let's see. Z hopefully was 4. Yes. And G, I'm hoping was, this G was 32.2. My diameter, the next to the last, was 0.5. And then the 0.75 for the length goes right in there. So if you're real meticulous about this, you can go through and figure out each one of these terms here. Now, here's what I'm going to do. I'm going to go in. Now I'm going to make this go away for a minute. I'm going to come back to the Matlab window. In Matlab, I'm going to call this A. I'm going to call this little a squared plus, this is going to be b squared, and this is going to be little b squared. This is going to be capital C squared. This is going to be a small c squared. This is going to be a d. I can't use d because I have d already defined as a symbolic, so I have to use e squared and then a little e, and then I'm going to use a capital F squared for this value and a little f there. And then of course I need to take a square root of it to figure out this value. Now we've already determined this. What we're shooting for is now, what is that? Now this may seem overly complex, but the whole point of this is I'm going to show you a simpler way to do this. Bring the command window back. Now use the arrow up key and I'll automatically determine what A is. There's A. What is B? B is the differential, looking down over here, it's the differential with respect to omega, or I mean not omega, WZ. So all I have to do is slip over here, change this to WZ. Up, and I messed up. That was A. WZ has to be renamed to a capital B. Capital C, I'm using the arrow up key. Capital C is the differential with respect to what? It's the differential over here with respect to Z. So I have a C. Now I need to take the differential with respect to D and make it an E. I've got to be careful about this. Capital E, differential with respect, and ironically, here's the D. So I'm taking the differential with respect to the capital D. Then I'm going to take the differential. I'm going to use my F out here, take its differential with respect to L. Alright, now I have each of my terms. What I don't have is my small a, my small b, my small c, small e, and small f. Now, I can look up here and realize these are my values for that, but I need to know my percentages. So I've sort of messed up a little bit, but I can figure these out. It's not that bad. I can sort of mess with my screen size here, and maybe I can shrink it down over here, maybe move it up here, and I can look and sort of decipher this, but I'll have to be very meticulous. What I'm about to do is this. Okay, let me get a drawing utensil. Here's what I'm about to do. I'm about to determine what is A. A is nothing more than this value, the uncertainty in G. So the uncertainty in G is nothing more than 0.5% times 32.1. That's got to be the value. Then that means B is the weight. Okay, so it's 30 times 4 over 100. That's B. This is A. What is C? Use Z. This. C is 4% of, 4 over 4%. Okay, wait, that was use Z. I just did that. E is nothing more than the diameter, 0.5, times its 3 over 100. And then F is the little f, that is 0.75 times 3/100ths. So I'm going to go into my Matlab window and type all these out. Now, unfortunately, when I hit this, all these terms are going to disappear, and I'm going to have to retype them. So I'm sorry about that, but that's, I guess, the other way I could do this. Here's what I will do. I'll go back in OneNote right here and rewrite these in black so that I'll have a record of these. So I'm looking for A. A is going to be, and I'm basically redoing the same thing. G is 32.1 times 0.5 over 100. B is equal to what? Well, B is the WZ, so it's 30 times 4 over 100. And C, what was C? C is nothing more than the Z, the 4 times 4 over 100. And then the little e is the, ironically, it's the D, 0.53 over 100. And the F is this length right here, is equal to 0.75 plus or minus, this is plus or minus 3 over 100. And then I'm going to put these now in Matlab. Now I have them all written out so I can bring up the Matlab window and this at the same time and not get myself too confused. So with that, let me see if I can find my command window. There it is. So now I can draw this back out and list my A is equal to 32.1 times 0.5 divided by 100, and I'm going to do them all together. So that'll suppress the output, but I'll go ahead and figure out what B is equal to. It's 30 times 4 divided by 100. And then what is C? It's equal to 4 times 4 divided by 100. And what is E equal to? It's 0.5 times 3 divided by 100. Hopefully I'm not making a mistake. I'm just talking as I go. 0.75 times 3 divided by 100. And there's all my terms. If you want to list them all, you can list them all. If you want to see them, but you don't want to list them, you can go to your workspace editor and look at everything there. At this point, there's my little a. Here, I'll get a indexing pen out. So here's my little a, my little b, my little c, little e, and a little f. There's my capital A, capital B, capital C. Now you have to remember these were created with the substitution. I took a differential of the equation with respect to its variable. I substituted for all these variables. They got substituted those variables. Okay, and here's E, and here's F. Now this answer is just carried along for the ride. It's always carried along for the ride, so it doesn't matter. Here's my symbolic variables. And at this point, I can go in here and figure out this term right here, this big square root here. Fairly simple to do. And let's go into this. I'll get rid of the this workspace for a moment, I can go back and get it. So what is the uncertainty in row? So square root of a squared times little a squared plus capital B squared times little b squared plus capital C squared times little c squared. Hopefully I'm not messing up. I'm going to go back and review. Now I have to go straight off to e, capital E squared times a little e squared plus a capital F squared times a little f squared. Now let's make sure I've done everything right. So okay, so what I've got is a capital A squared, little a squared, plus capital B squared, little b squared, capital C squared, little b squared, E squared, little e, capital F, little f, taking the square root of the whole thing. Let's see what we get. Okay, so the answer is 0.45. So let's go in here and say it's 0.45. So my answer should be this plus or minus 0.45. Now, is there another way to do this? And to pre-answer that question, I would say yes, there is a better way. Let's suppose something like this. Let's suppose, first of all, why you would want to do it a different way. Let's say instead of rho being a function of 5 variables, let's say it was a function of 100 variables. Or say it was anything. Say some pi was a function of 100 variables. So this would be 100 long. This thing would be a mess. It'd be 100 long. You'd have 100 variables across here that you'd have to do. And you'd have to take the partial of each and every one of those. And let's say we have a nice equation here. This is a very nice equation. It's straightforward. It's easy to see, but let's say you had substitution upon substitution, and say they were nonlinear, and it was difficult to substitute in them. So you had to calculate something, then calculate several things in a row, and you had several equations. So what you're going to have to do is take multiple levels of differentiation. Cause a lot of problems. So let's take a different approach. Let's take the approach that with ours. I'm going to take my equation and I'm going to list it down here, and I'm going to list all of my variables and uncertainties thereof in here. So here's what I'm going to do. I'm going to go in and try to see if I can simplify things. Let's get some of these annotations off here, and then I'm going to copy things down. And so in a minute you're going to see, I'm going to pause it and it'll come back with everything in one particular location. Remembering, of course, that our goal is right here. This is our goal, or better yet, here is our goal. Okay, so I'm going to pause it. In a second you're going to see everything flashing up here. Now I'm looking at everything and I'm listing all this. This is my equation, and these are my variables going into the equation. Now previously I listed them as a percent, plus or minus percent. What I want to list them now as is the actual variable, plus or minus what number. And it turns out that happens to be the A, B, C, D, E, and F. Not the D, but it's A, B, C, E, and F. So if I'm looking at, for example, the WZ, it's 4% of that. So if I go back and look at this and pay careful attention to what I'm looking at, let me sort of write these down. First I will go over, I'll bring up the command window. Or better yet, a better window to come up with is the actual window here, because the uncertainty, the plus or minus, are listed here in A, B, C, E, and F. Now I'm going to move this window over to the side so that I can read them off and write them directly down. First of all, what is the WZ? Plus or minus what? Well, it turns out, you look up here, it's the B. The B is 30 times 4%. So the little b ends up being 1.2. Okay, so the Z, for example, the little z, where is it? It's right here. It's the C, which is 4 over 4, so the C is 0.16. Now these are not percents, these are actual values. It's 30 plus or minus 1.2 pounds. Okay, G. G happened to be the A, which ends up to be 0.1605, and there's probably extra change, but I'm not going to use the extra change. D turns out to be the value of E. It turns out to be 0.0150 and some extra change. Not going to use it. And this one ends up being 0.0225. Now, how can I come up with the same or very close to the same values up here without taking differentials at all here and just using this information? Here's what I'm going to suppose. Okay, the whole goal here is to look at what the values are in the distributions. So here's a 0. This is WZ, for example. Now, here's our 30, but we actually have a distribution about that 30 in which the first standard deviation becomes 1.2. How do we represent this in Matlab? Well, first, let's take a look at a Matlab function, two Matlab functions, in fact. And I may have to use the help, but the first Matlab function, here, let's see if I can get it down and out of the way, is, let's say we have x, or here, let's see, how would I do that? At this particular point, I guess, there's no reason for me to save any of my variables, so I can clear the memory and continue to work my problems. I have everything stored in my command history, so I can go back to this at any point. So I'm going to hit a clear. And now I'm going to basically look at WZ. Now what I'm going to say is, let's say WZ is equal to RANDN 100,000 by 1. And then I'm going to do a histogram of WZ with 30 bins. Now, the plot appeared over there, but I'm going to drag it back here. Now, what you see, and let me spend some time telling you what you're looking at. You're actually seeing that, and this is not correct per se, because my average should be 30, but my average is not. My average is 0. Turns out if you go over here, one standard deviation away gets you there to your 1. I'm not drawing straight lines, but that's one standard deviation. What you see is this nice bell-shaped curve. It doesn't look that nice, so let's try to make it look nicer. How do we make something like that look nicer? Well, here's what we're going to do. I'll go arrow up twice, and I'm going to put that many more values in it. Arrow up twice. Now, here's what you see. I basically didn't change the look of it, but if I go in, arrow up twice, and put 10 million data points, and then instead of 30 bins, I'll put 100 bins, what you see is looking very much like a Gauss distribution. Now, what is the average of WZ here? pretty much 0. What's standard deviation? 1. So what can we do to convert this? Well, let's say we did something like this. 10 million, well, 10 million may be excess. How about a million? Because I don't want to spend a lot of time here. 30 plus, now what was my plus or minus here for? It was 1.2. 1.2 times that. Now, standard deviation, oh, surprising, 1.2. Mean, 29.9, pretty much what I'd expect. What does the histogram look like? Looks like that. Take a look here. What you're seeing is a mean of about 30, and this distribution that is created by this. You clip it off, and you'll get one standard deviation on either side. I'm, again, not drawn very well. Majority of the points fall in this category. There are some outliers that are possible here, so it could be greater than 1.2, but this is statistics. There's always a chance it could be way out on the outside. So this gives us an idea of how we can distribute all of our variables. All we have to do now, so let's do this for the rest of them. Here, z is equal to, here, let me use the backspace arrow up key. Now one of the things you have to do in this is the actual number of experiments. Think of this as being 1 million experiments. There's 1 million data points on this, and each one of these, if you're running an experiment, you're going to take the same number of this. There's 1 million of those, 1 million of these, 1 million of each one of these. So just remember that this value has to be the same. Only thing that changes is this will become that, and 30 will become 4, and WZ will become Z. Then you go through this process again, where this becomes G, 30 now becomes 32.1, and 1.2 becomes 0.1605. And we're going to do this until we obtain all of our values here. So let's do this real quick. Okay, so I did the arrow up key, slide back across. I'm looking at Z. It is not 30, but it is 4. Its first standard deviation is 0.16, and you got it. Okay, one more. Go to G. Okay, so its plus or minus is 0.1605. Its mean value is 32.1, and it is not Z, it is G. D, its first standard deviation 0.015, and it is 0.5. Oh no, I messed up. Okay, I didn't change it. Okay, here, change it not to G but to D. I fixed the G by arrowing up twice there and picking that one up. Now let's fix the last one. 0.225, and its value is 0.75, and it is L. So if you look at what I have in my workspace, I have D. I have 1 million values of D. Here, let's bring out the annotator here. I have D. I have 1 million values of D. I have 1 million values of L, 1 million values of the weight, 1 million values of G, and 1 million of Z. The answer is just something that was carried along from this right here. All right. Now, simple equation. Let's see if I can find it in my history. And you have to give me a second here. Okay, it is this equation. See if I can drag it over into right there. Okay, so what I'm copying is something from my history, and hopefully, let's check this. Is this that equation? So WZ minus Z divided by G divided by this value, pi d squared over 4 times L. Alright, so I believe I'm okay. However, when you type this in and hit enter, it's going to give you an error. Oh, first error it's going to give you is out of memory. I don't have enough memory in this machine to do this. So, second thing is, it may have given me a different option had I put the period in here. And hopefully I'm putting it at the right place. Okay, well, let me hit the Control C and do it again and put that. So, what you've noticed now, maybe you have, maybe you haven't, here. This is an element by element operator, which says something like this. Let's take a look right here. Let's say we had D equaling to 1, 2, 3, and 4. Instead of 1,000,000 elements, you had that. D squared won't work, but a D period square lines them up like this and lines up 2 D's and squares them and becomes 1, 4, 3 them 3, and list them like that. So what it is it's an element by element multiplier. Now the reason it didn't work before is it tried to multiply matrices, and that's what it threw it out of memory. But also notice this. I now have a row which has 1,000,000 elements in it. Here is your key. Here's the whole point of what we're doing. Go in here now and do a histogram on row with 100 bins, and what do you get? You get about 5.5. Interesting. And there's a distribution associated with it. What's the mean of the distribution? 5.5196. What is the standard deviation of the distribution? 0.45. So according to this, 0.453. So according to this, let me slide it over so I can copy it out. According to this, row, if I just shove distributions into here, ends up with 5.5196 plus or minus 0.4530. Interesting, because if you look back up here, it's 5.5, 2 zeros and a 2. So we're off here, we're off here. But here's the situation. Which one is more accurate? I contend that this one has a higher level of accuracy. This is just supposition. I'm not proving anything. But the other thing might be that if you start looking at a distribution, you start looking at your figure, you get a better feel of what's going on. You actually can look at this. They always say a picture's worth 1,000 words. It may be worth more than 1,000 words. Here's your mean, and then here's your standard deviation. If you look at this fairly closely, it appears like there's a little bit of a skew in this. If you look, here's your mean, it looks like it skews longer over into the tail is larger over into the right. This is something you'll see in this that you won't see in the other analysis techniques. Okay, so for what it's worth, that's an hour-long lecture, roughly an hour-long lecture, where I go through an actual experiment and come up with the entire process. Pretty much is not a lot of information there and on this lecture board that you see, but hopefully you will have gotten enough to be able to do the assignment.